Well, hello you guys, how are you? Today we are going to go over lesson 9.2.4, which is covering the idea of real numbers. And it sounds like a silly title, in my opinion, because what are fake numbers if we're looking at real numbers? And believe it or not, when you get further in your math career in high school, you are going to work with numbers called imaginary numbers. So for right now, everything we've done in math all the way up to 8th grade has been working with real numbers. So today we're just going to break real numbers down into different categories and just find out what are some examples of numbers in each of the categories. So the first subcategory of real numbers are rational numbers. And rational numbers are most or the majority of the numbers that we work with. Rational numbers are defined as numbers that can be written as a ratio. And remember that ratio is just another word for fraction. Okay? And not only can they be written as a ratio, if you wrote them as a decimal, rational numbers end. Really, we say in math that they're terminating numbers, meaning like 4.5 is a terminal decimal. It has an end to it. Or if they don't end, they repeat, like 0.333333, etc. Okay? So rational numbers can be written as a ratio or a fraction, and as a decimal they end or they repeat. So some examples of rational numbers. -1/2. That is a number written as a fraction or a ratio. +5 is a rational number. We could write this as a fraction if we had to. It would just be 5/1. -12 is a rational number. Square root of 36 is a rational number. We learned in our last lesson, if you take the square root, it means what number times itself equals 36. So this would simplify to 6, which is a rational number. The other section over here that I have a smaller part dedicated to is for irrational numbers. Irrational numbers. Irrational numbers cannot be written as a ratio or can't be written as a ratio. Remember, that means a fraction. And as decimals, they don't end or they don't repeat. Probably the most famous irrational number, in fact here we dedicate a whole day of math class to this, is pi. We celebrate Pi Day. So we call pi 3.14 when we approximate it, but in actuality pi is that never-ending decimal that goes on and on and on and on, and it never repeats. Now if you multiplied pi by itself, or pi squared, that would be irrational. If you multiplied pi by any number, it would still be irrational. Some square roots are irrational. If you play with your calculator on these, you'll see if you found the square root of 2, it's a decimal number that does not end and it does not repeat. Another example, square root of 17. So irrational numbers, they cannot be written as a fraction or a ratio. I just noticed I had a little spelling error there, not ration, but ratio. And as decimals, they do not end or repeat. Now the group of irrational numbers, we can't break that down into any smaller subcategories, but we can go back to rational numbers and break that down into some smaller subgroups. So I'm going to come back over here and we're going to make a little section here for a subcategory of rational numbers. And that category of numbers are integers. Integers, I guess I would informally define them as positive or negative numbers, but positive or negative whole numbers, if that can be used as a term. So like negative 15, positive 20, 3, negative 10, 0. Those are all examples of integers. Notice no mixed numbers here, no decimals, no 15 and 2/3 type of numbers. Okay. Then the group of integers can be broken down into a smaller category. And these numbers are called whole numbers. Whole numbers, well, the smallest whole number is 0, and then 1, 2, 3, 4, etc. Those are whole numbers. So not necessarily all positive, because 0 is neither negative nor positive, but 0 and all positive whole numbers make up the set of whole numbers. And then the last category that we're going to break our real numbers down into are called the counting numbers. So if we were back in regular school and sitting in our classroom together and I asked you to count the number of students in the room, the first number you would say would be 1, then 2, 3, 4, etc. The only difference between the whole numbers and the counting numbers is 0. 0 is included in whole numbers, 0 is not included in the counting numbers. Okay, we are ready for our first example problem. It asks us just to determine if each number is rational, so would it be somewhere on this right-hand side of the chart we created, or irrational, would it belong over here on that side? So, first one I'm looking at is the square root of 6.25. I'm going to grab my calculator and enter 6.25 and then find the square root, and it looks like it is 2.5. That is a decimal that terminates or ends, which means our answer is a rational number. Next one, square root of 100. I don't need my calculator for that one because I know 10 times 10 is 100, and 10 is, well, it's an integer or a counting number or a whole number. It's all of those categories that we had listed over in our column up here on the left-hand side, which are rational numbers. Okay, square root of 7. Let's see, I'm going to go to my calculator for that because I'm not aware of a number times itself equal to 7. Oh, 2.7 0.645751311. Okay, so it looks like this answer, we don't get an exact answer because it's a big long decimal that doesn't appear to end. It only ends because the screen of my calculator runs out. It rounds to about 2.6, but when I'm looking at this, I don't really see a repetitive pattern right now at that point, so I would make my best guess that this is irrational. Next one is -5/9. Okay, I know from the very first thing I wrote about rational numbers that they can be written as a fraction. So that tells me this must be rational because it's already written as a fraction. Okay, let's go over here to these 4. Next one we have is square root of 76. I don't have that one memorized, so on my calculator I'm going to find the square root of 76. Okay, it is a big long decimal number again. So it's not really equal to, I'm going to say it's approximately 8.7, but looking at this, again, I see a decimal number that doesn't really have any repetitive pattern going here. So again, my best guess is that this is an irrational number. Okay, 6.4 times 10 to the second power. So if we look back up here into this chart, on either side, we did not have any numbers whatsoever in scientific notation. So I'm not really sure what to do with it when it's in this form. But I know that I can change a number from scientific notation into standard notation. This is telling me that I would need to multiply it by 10 twice, or by 100, which would in essence move my decimal over 2 places, which means 6.4 times 10 squared is equivalent to 640, which is a counting number or a whole number or an integer or a rational number. Okay, next one, it's written as a fraction, so that one's easy right off the bat. Because it's written as a fraction, I know that it's rational. Okay, last one, we have negative square root of 81. Not super sure because we had some square roots listed on the irrational side up here when we were talking about the different categories. So I'm going to look at 81, and I know that I can simplify that because 9 times 9 is 81. That means the square root of 81 is 9. I'll write it over here. But this one is being multiplied by a negative, so that means if I simplified it, I would get -9. -9 is an integer, which is considered one of the subcategories of rational numbers. So our last one, negative square root of 81, is rational. Moving on to example 2, we are asked to write each rational number as a simplified ratio. So each of these numbers is a decimal number, which is a rational number because they terminate or end. And they want us to write it as a simplified ratio, so that means as a fraction in simplest form. So let's take a look at this first one, 0.19 or 19 hundredths. The 9 is in the hundredths place, so I know that will be the denominator of my fraction. And then this tells me that there are 19 hundredths, so 19 becomes my numerator, and I don't believe that that can be simplified. So there's our answer written as a simplified ratio. Okay. Next, let's move across to 0.391 or 391 thousandths, because the 1 is in the thousandths place. So I know my denominator will be 1,000 because that's the place of the last number, and then my numerator is 391. Once again, that number cannot be simplified or reduced, so there's our simplified ratio. Next, 0.001 or 1,000th. Again, our denominator is the thousandth, and it's just 1,000th, which cannot be further simplified, and there's our answer. Okay, moving down to the next row. We have 0.019 or 19 thousandths again. So my denominator is in the thousandths place. There are 19 of those thousandths, and this also cannot be simplified. I wonder if any of these will. Next one, we have 0.3 or 3/10, and if you say the decimal number mathematically accurate, you hear what the fraction should look like, 3/10. 3 is in the tenths place, so 10 is our denominator. We have 3 of those, and that cannot be simplified any further. Last one, 524 thousandths. Okay. Our denominator is 1,000. Our numerator is 524. Both of those are even numbers, so you could divide them each by 2 to simplify, but I happen to know that 4 goes into both of these. I know 4 goes into 1,000 evenly, 250 times, and 4 goes into 24, the last 2 digits there, so I know 4 will also divide evenly into 524. So 524 divided by 4 is 131, and 1,000 divided by 4 is 250. And I believe that is as simplified as we can write that ratio. Okay, for example 3, we're going to look at how to write a repeating decimal as a ratio or fraction. And we're going to start just by taking a look at this decimal. 0.57 with a repeatant. This is a rational number because it is a decimal that repeats. In other words, 0.57 with this line or bar over it tells me that these numbers would repeat on and on and on. So 57, 57, 57, and we could keep going and going and going as long as we wanted till we got bored, which I am, so I'm going to put ellipsis there. But you get the picture. You could see that this just pattern repeats again and again. So 0.57 is this equal to 57 hundredths, because the 7 ends in the hundredths place, right? So I put it over 100, and it's 57 of them. So let's test that on the calculator. What I'm going to just do, let me see if I can slide it all the way up so you can see. There we go. 57 divided by 100 is 57 hundredths. So that worked because we terminated our decimal here. When I entered it on the calculator and did 57 divided by 100, I did just that, 57 divided by 100. But if I did 0.57575 divided by whatever, wherever I stopped, it would not be exactly equal to 0.57 because we have all of this after the 57. This is an approximation. So what we need to do is figure out, when I want to get the exact answer, how would I write this as a ratio? So what we do is let's start over again. Let's start with our number 0.57, and the repeating ends in the 100ths place. So what we do is take whatever place the repeating stops in and subtract 1 from it. In other words, what is 100 take away 1? Hopefully you said it's 99. So that is what we are going to put as our denominator, 99, and then our numerator is 57. Now, let's take a look at what happens when we divide 57 divided by 99. We get exactly this number. No estimating like we had to do here. So, to repeat, wherever the place is that the pattern stops repeating, in this case it was the hundredths place, subtract 1 from it and that becomes the denominator, and then your number that repeats is in the numerator. So that is how you would write 0.57 with the repeatant as a rational ratio. Okay, let's continue on with example 3. We are being asked to write 4 different repeating decimals as ratios or fractions. So looking at this first one, we have 0.524 with the repeatant. So the last repeating number is in the thousandths place. So I subtract 1 from that. 1,000 take away 1 is 999. That gives us our denominator. And then our numerator is 524. And you could check your answer on the calculator by taking 524, and I'm going to hit the divided by button. 999 equals, and there we have 0.524, 524, 524. Exactly what we started with here. Okay, next one. We have 0.7 with the repeatant. Okay, the last digit in the repeating section is in the tenths place. So we take the tenths place and we subtract 1, which is 9. And our numerator is 7. So now let's check our answer and do 7 divided by 9. And there it is, repeating sevens. Next one, 0.019. My last repeating digit is in the thousands place, so I'm going to do 1,000 take away 1. That gives me my denominator, 999, and there are 19 of them. So it is 19 over 999. I'm going to check my answer again. 19 divided by 999, 0.019019. Perfect. All right, last one. 0.65 with the repeatant. The last repeating digit is in the hundredths place, so I'm going to do 100 take away 1, which is 99. So as a ratio, this would be 65 99ths. Let's check that. 65 divided by 99, and it equals 0.65 repeating. 0.65, 0.65, 0.65, etc. And there you have it, how to change a repeating decimal into a ratio. That is the end of today's lesson. So, tomorrow, if you're following our calendar for April, tomorrow your assignment is to complete Review Preview Problem 9/110. That's it. Just one problem for tomorrow's assignment. Have a great day. I'll talk to you soon. Remember to email me if you have any questions or need help.